Okay, I'm Stephen Herwig. I'm an assistant professor at William and Mary. I'm a systems security researcher, and this is sort of my first foray into the space field. And today I'll be presenting a proposal or position type of talk. Okay, so as we renew efforts to explore our solar system, there's an increasing need for robust communication with the growing collection of deep space objects. Unfortunately, the internet doesn't work in deep space. Extreme distances, lack of continuous connectivity, and high error rates violate key assumptions of the internet's protocols. To meet these challenges, NASA, in cooperation with other national space agencies, is leading development and standardization of the protocols for the envisioned Interplanetary Internet, or IPN. This is a collection of interoperable deep space networks that will seamlessly connect with the terrestrial internet. The IPN's main protocol is called the Bundle Protocol, or BP. So just as in IP we have packets, in BP we have bundles, which carry the message and all its routing metadata. BP is based on delay-tolerant networking, which means that it's a message-oriented overlay network that uses a store-and-forward model. Each node in the path stores a message until there's an opportunity to forward it. The communications, but the IPN also needs to provide secure communication. Being an extension of the terrestrial internet, the IPN adopts the internet's threat model of an on-path attacker. However, for the same reasons that TCP/IP doesn't work in space, TLS also doesn't. To address this, BP added a generic security extension called BPSec to ensure the integrity and confidentiality of a message. The problem that I want to highlight today is that BPSec itself doesn't specify how an application would apply the BPSec extensions. In this talk, through a series of thought experiments, I'll examine a few use cases to argue that BPSec is either insufficient or non-optimal. As we go, I'll enumerate requirements for extending BPSec to support these use cases, and then I'll propose one such approach. First, communication. Imagine that an operator on Earth wants to send a message to a group of devices in space. The first issue is that the operator may not even know the identifiers for the group members. In the terrestrial internet, we might use a name service to help with group enumeration, but such a service requires a lot of round-trip communication. Due to the high latencies of space communication, our candidate protocol has a requirement to favor non-interactive approaches. Assuming the operator can enumerate the group, the second issue is how to deliver the message confidentially without additional bandwidth overhead, namely without having to separately encrypt the message to each member. Okay. The device in deep space that sends encrypted data to a laboratory on Earth. Since the device is low powered, the device first routes the message to a high powered relay. To conserve bandwidth, the relay should only transmit the valuable data and discard the others, without observing the underlying plain text. In other words, given constraints in processing data at the endpoints, protocols need to support the secure offloading of processing to the network itself. As our final example, imagine that an operator wants to anonymously communicate with a spacecraft. On the terrestrial internet, we could use Tor to set up a tunnel. We could achieve something analogous with BPSec, but there are two drawbacks. First, setting up a tunnel is a very interactive operation. And second, it requires the client to have a global view of the network so that they can select a route. In contrast, in space, protocols need to tolerate having only a partial view of the network. When looking at these requirements, functional encryption really stands out as a useful primitive to consider adding to BPSec, precisely because it is non-interactive, it has efficient implementations, and it allows for delegation and decentralization. To quickly review functional encryption, or FE, the FE setup is that a user Alice has a public encryption key and a primary secret key. And given the description of some function F, Alice can use her primary secret key to derive a secret key associated with F. If Alice encrypts a message X with her public key, and Bob decrypts this message with the function key, Bob only learns f of x rather than the entire message at x. So functional encryption allows Alice to selectively share data according to an access policy that F expresses. In fact, two important sub-branches of public key cryptography can be recast as special cases of FE. The first is identity-based encryption, which is where any string, like an email address or a domain name, can effectively serve as a public key. Alice encrypts her message with this string, and Bob's function F only reveals the message X if the string comparison succeeds. The second, attribute-based encryption, is similar, but now Bob's key encodes Bob's attributes, and Alice encrypts her message with a policy over the attribute space. Bob only learns the message if his attributes satisfy the policy. My proposed design for extensible security in the bundle protocol incorporates FE for two purposes: endpoint naming and network functions. BP already uses URIs as endpoint identifiers, but to secure communication and reduce reliance on centralized services, I propose a URI scheme that incorporates identity-based encryption. For instance, the URI curiosity.mars.nasa.gov means that both the identifier and the public key for the Curiosity rover is its domain name. Returning to our earlier example of group communication, a wildcard such as star.mars.nasa.gov instead means two things. First, that the endpoint is a multicast group of all subdomains, and second, that the group is encrypted to the group public key, star.mars.nasa.gov. And finally, to allow greater expressivity, the scheme also incorporates attribute-based encryption. So if we had a message that was intended for all Spanish cameras on NASA Mars equipment, then a URI like the one shown here would mean that the message is doubly encrypted. One layer of encryption for the multicast endpoint, another layer for the camera attribute. While our naming scheme supports rich destination identifiers, we also need intermediary nodes to provide rich services over our bundle's encrypted data. We propose the development of a BPSec extension that specifies the following. In FE operation, the parts of the bundle that's small and interprets the results. Returning to the earlier example of a low-powered device transmitting encrypted data, we imagine that the device sends the high-powered relay and bundle that contains not only the encrypted data, but also a bundle filtering program. And finally, applications can compose the endpoint identifiers and the FE programs. Returning back to the anonymity use case, rather than source select a precise tunnel, the user's bundle instead uses our flexible URIs to specify an acceptable set of relays for each hop in the tunnel, along with an FE program that computes a routing metric to help a relay select the best next hop amongst this set. Since our proposal is fundamentally pushing functionality into the network, it brings up several challenges. The first is routing. Because it has to grapple with a difficult trade-off between establishing routes and minimizing resources. What this proposal adds to that research is the first-class concern of constructing multicast trees based on our semantically rich endpoint identifiers. And the second challenge is in running untrusted FE programs. There's a long history of techniques for sandboxing and automatic verification of a program's safety, and our initial focus would look to integrate eBPF, a bytecode that the Linux kernel uses extensively, into the BP stack. And finally, although BPSec considers key management to be out of scope, it's obviously a very important part of the ecosystem, and we need practical schemes for things like revocation and forward secrecy. In summary, today I proposed amending the security extensions of the Interplanetary Internet to include support for functional encryption. With such support, I've argued that we can express a variety of communication use cases while still satisfying the latency and bandwidth constraints of space networks. I've enjoyed the workshop so far, and with that, I'll take any questions.
Hi, thanks for your talk. How would this system be resilient towards standard attacks on like IP protocols like DNS poisoning and stuff like that?
That's a good question. Because at the heart of it's a sort of identity-based encryption. The delegation of that looks a lot like it does in the domain name system, where you have like one key generator delegating the generation of keys for subdomains. So I think there's you bring up good points about like open questions and to ensuring like the that the authentication of nodes when they actually sort of register for a domain name, and then also making sure that the information regarding the domain names themselves are consistent. There's a consistent view of that within the network. So I agree with you. I think those are open problems.
All right, more questions? Sure.
Yeah, can you tell us something about the performance overhead that this functional encryption would actually carry? How much more expensive is it compared to a simpler encryption scheme?
Right. There are several implementations. The one that I was looking at most recently, of course, it depends a little bit on the security parameters, but encryption was around a second to encrypt a message, and like decryption was, I forget the exact message size, but decryption was under 100 milliseconds. The processes are take too long for like the normal internet, but if we're talking about things that are in the granularity of a second or 100 milliseconds, I think that's totally within purview of something like the Interplanetary Internet.
Yeah. So you have this example you were showing about your smaller satellite that's sending data, and it's a low power, so you're going to forward it through a bigger thing that's more powerful. That's going to include this program with it to validate the data, right? But I guess, can you help me understand this a little more? Because you're arguing that this data could be corrupted in transit, so I need to filter it with a program that's also potentially corrupted in transit?
Right. I mean, the idea there would be that the low-powered and the high-powered devices are wanting each hour the power to actually like form a link over an extended distance. So what I was just trying to motivate there is having a higher powered device perform some of this initial processing and filtering on behalf of the maybe just a smaller low powered sensor.